My name is Ramasesha. I am from the Solid State and Structural Chemistry Unit of the Indian Institute of Science in Bangalore, and this course is about electronic states in solids. I basically will introduce you to the concepts of energy band theory more from the point of view of a chemist, and I will then introduce a little bit of the phononic band structure or the lattice vibrations, and as we go along you will come to know more about it. So, I have called this course bonds and bands in solids. So, as you know, a solid is made up of many electrons and many nuclei. So, if you write down the Hamiltonian of a solid, it is going to be pretty complicated. Let me just write down for your benefit. So, H total, I call it T, which is actually the kinetic energy of the electrons plus the kinetic energy of the nuclei plus the electron nuclear attraction term plus the electron electron repulsion term plus the nuclear nuclear repulsion term. And I can write down the E operators for each one of them. T electron is actually minus h cross squared by 2m sigma over I del I squared, and the nuclear kinetic energy is just given by minus h cross squared by 2 sigma over alpha del alpha squared divided by m alpha, and the electron nuclear attraction term is given by V electron nuclear is equal to minus sigma over alpha sigma over I z alpha E squared upon R I minus R alpha, and the electron electron repulsion term is given by sigma over I sigma over j greater than I E squared upon R I j, where R I j is equal to the distance between the electrons I and j, and then I have similarly the nuclear nuclear repulsion term, which is just given by sigma over alpha sigma over beta greater than alpha z alpha z beta E squared upon R alpha minus R beta, where R alpha runs over the indices runs over the nuclei and I runs over the electrons. So, that way whenever I use alpha or beta, it is actually I am referring to the nuclei, and whenever I use I or j indices, then I am using the coordinates of the electrons. Okay, so now this Hamiltonian is too complicated, too very complicated to solve the Schrodinger equation, which I can write in the Schrodinger equation, which I can write as H dot psi. I will use the double bar for writing the psi just to distinguish with other wave function psi, which I will be using quite frequently. So, this, and I will use curly brackets to represent the collection of all the electron coordinates. Similarly, the collection of all the nuclear coordinates within the curly brackets of capital R, and this is equal to E dot psi R comma R. So, as I said, this is a rather complicated equation and you cannot really solve it analytically. Analytic solution is only possible for very few systems like the hydrogen atom in the electronic problem, or some other model Hamiltonians about which we will not discuss much in this particular course. Okay, so, what is it that you want to do? How will you go around simplifying the Hamiltonian? What are the approximations that are made to simplify this Hamiltonian? So, I will talk about the approximations for simplifying the Hamiltonian. The first approximation is called the Born-Oppenheimer approximation. Born-Oppenheimer approximation this is also known as the adiabatic approximation. I will tell you why. The second approximation that one does is what is called the independent particle approximation. Independent particle approximation. You can also call it the orbital approximation. That is the independent orbital approximation. Well, in the Born-Oppenheimer approximation, what one does is the following. In the BO approximation, we assume that the total wave function, which I wrote as psi r can actually be written as a factor of two terms. So, one is the psi of the electronic part and dependent on the nuclear part, and I will tell you how it is going to be dependent on the nuclear part as we go along, and then multiplied by the nuclear wave function, which is just dependent upon the nuclear coordinates chi of r. So, supposing I substitute this Hamiltonian this into the the Schrodinger equation, then what I get is the following. So, let me see h psi r equal to h psi r dot chi r can be written as the because the first term in the Hamiltonian, which is this one, the first term in the Hamiltonian, which is this part that I am showing, is not going to act upon the nuclear coordinates and it only acts upon the electron coordinates, and of course this term acts only upon the nuclear coordinates. So, because of that I can write it in the following fashion. I can write it as minus h cross squared by 2m. Well, let me write it a little bit differently. So, I can pull chi of r all the way through, and I can write it as minus h cross squared by 2m sigma over I del I squared minus sigma over alpha sigma over I z alpha E squared upon r alpha minus r I plus sigma over I greater than j E squared upon r I minus r j. This acts on psi r comma capital R, and then I have another term which is a nuclear term, because the electronic coordinates will be pulled through, and of course I will tell you that I make an approximation in doing that, and I will tell you what is the approximation I am doing. So, plus I have psi of r comma r, which I have pulled out, times minus h cross squared by 2 sigma over alpha 1 upon m alpha into delta alpha squared plus sigma over alpha greater than beta z alpha z beta E squared upon r alpha minus r beta. This one acting upon chi of r, and I have two terms which I have not included, which comes because of the, let me go to the next page, and then I can write down the next one as minus h cross squared by 2m sigma over alpha 1 by m alpha del alpha psi r times del alpha chi r, which is actually a mixed term, which is a mixed derivative that you will get. And I have another term which is minus h cross squared by 2 sigma over alpha 1 upon m alpha chi of r, which I have pulled through all the way, times del alpha square psi r comma r. So, now what I will do is the following. This is actually equal to, this is a Schrodinger equation. So, this is equal to E total psi r times chi of r. Now, let us look at the first term in the first line in the Hamiltonian or in the equation that I have written above. So, it looks, this particular line actually looks as though this is just an electronic Hamiltonian if I fix the nuclear positions at alpha. That means, as long as I treat the position of the nuclei parametrically, that means I fix every value of the nuclear coordinates while calculating the wave function psi, and when I want to find out the wave function for a second nuclear set of nuclear coordinates, then I will change the nuclear coordinates to a new set and again calculate this electronic Hamiltonian. Then I can think of it as though the Hamiltonian here is an electronic Hamiltonian in which the nuclear positions are frozen or treated parametrically. So, I can actually write the following equation, which is quite simple to understand. So, what I have is the electronic Hamiltonian H electronic is equal to minus h cross squared by 2m sigma over I del I squared, and then I also have minus sigma over alpha sigma over I z alpha E squared upon R I R alpha minus R I plus sigma over I greater than j E squared upon R I minus R j. And I can solve this for fixed nuclear coordinates, and I can write down my Schrodinger equation in that case as H electronic psi r or fixed. I have used a subscript f just to emphasize the fact that I have actually frozen the nuclear positions at specified values, and this will now be actually the electronic energy, which now depends upon the frozen nuclear positions, because as you change the nuclear positions RF, then you are changing the energy. So, this is actually a position dependent nuclear position dependent energy E R E times psi of R comma RF. Now, what I can do is that substitute this in the equation that I wrote down above for H total. And so what we will do is the following: substitute this in the first line of, let me call this equation number as 1, in the first line of 1, and rewrite my Hamiltonian or the Schrodinger equation, in which case I will get H total psi r comma r as equal to chi of r, because I am going to pull it through, it is not dependent on this in the first line, times E electronic or fixed times psi r comma rf, and then I have plus psi r comma rf times minus h cross squared by 2 sigma over alpha 1 upon m alpha del alpha squared plus sigma over alpha greater than beta z alpha z beta e squared upon r alpha minus r beta times chi of r if we neglect the last line in 1. So, you see here is the last line in 1, which is actually this line. So, if I neglect this line, this gets replaced by E electronic times psi r comma r, and this is again psi r comma r times chi of r. Okay. So, and of course, I should have been a bit more careful in what I wrote. So, I should have actually written down this one as I should have put a chi of r here. So, let me put this and correct it. Okay, so that is what it will be like, and now let us see what you can do. Now what happens is you can we can cancel the chi of r, rather the psi r comma r on both sides. So, this will be equal to E total times chi of r psi of r comma r. Okay. We can cancel psi r comma r from both sides of the equation to get the following. So, what we will get is minus h cross squared by 2 sigma over alpha 1 upon m alpha del alpha squared plus sigma over alpha greater than beta z alpha z beta e squared upon r alpha minus r beta plus E electronic as a function of r frozen times chi of r R is equal to E total chi of R. Okay. So, what we have actually done is we have got two different Schrodinger equations. So, one of the Schrodinger equation that I have is the electronic Schrodinger equation. Let me highlight it here by using the highlighter. So, let me highlight, sorry, I am trying to find the highlighter on this one. So, yeah, okay. Yeah, I found the highlighter. So, this is the electronic Hamiltonian, okay, and this is the electronic Schrodinger equation that I have, which is for fixed electronic coordinates or rather nuclear coordinates, and then I have the total system or the total Hamiltonian, which is approximated and which is given by this, which depends upon the electronic state parametrically. That is, I have to get my expression which is the following, that is, I have to get this term I have to get from the electronic solving the electronic part of the Hamiltonian, substitute it here and then calculate the vibrational energy levels. And when you actually are substituting this here, one must remember that you have many different electronic states. So, you have to specify the electronic state energy or the potential energy surface corresponding to the electronic state, and what it means is that your vibrational energy levels depend upon the electronic state in which you are calculating those. So, if you are in the ground state of the electronic system, the vibrational frequencies will be different than when you are in the excited state of the electronic systems. So, we will talk more about it later on. Now, there is something that I have actually brushed aside under the carpet, which I have to revisit, which is basically the terms that I have neglected. So, now the terms that we have neglected are the following. Terms are which I will call actually the perturbing Hamiltonian H prime, which has the following terms, which is minus h cross squared sigma over alpha 1 upon m alpha del alpha psi r comma r times del alpha chi of r, and the second term is of course minus h cross squared by 2 sigma over alpha 1 upon m alpha chi of r then I have del alpha squared psi r comma r, and here of course I should have been careful and I should have written this thing as h prime psi r comma r, and then so now let us see what is the contribution of H prime to the energies. So, how serious is the approximation, in the sense that have we neglected things which are very important, and we have made an approximation which is not of the right magnitude. So, this is what we really have to look at. So, in order to do this, what we will do is we will calculate the expectation values of H prime in the state the expectation value in the state. So, in order to do that, what I will do is what does the first term give? What the first term gives is the following. The first term gives the expectation value, gives the diagonal element of the diagonal element as minus h cross squared by 2 sigma over alpha 1 upon m alpha integral psi star r comma r times del alpha psi r comma r d cubed r, because I have separated the coordinates, and then multiplied by integral chi of r del alpha chi of r d cubed r. Now, let us look at the first term. So, if I look at the first term, what happens is, so I am going to focus on this term. Okay, when I focus on that term, what I will see is the following. That is, this can actually be written as, actually it is del alpha times integral psi star r comma r psi of r comma r times d cubed r times integral psi star, rather chi of r del alpha chi of, let me write it neatly just so that. So, d cubed r. So, what you find, this one is actually the number of electrons in the system. So, because it is actually the number of electrons in the system, it is a constant, NEL is a constant, and hence del alpha NEL is equal to 0. So, the expectation value of the first neglected term is 0. So, the approximation is safe so far, so no problem. We will continue with this in the next class. Thank you.